Hello everyone, welcome to my second video on trigonometric integration. So in the first video we saw integrals of the form sine times cos with different exponents. In this video here we're going to look at integrals of the form tan times secant. Okay, and we're also going to look at the integrals of the form cotangent times cosecant. And we're going to observe the strategy, which are very similar in both cases. So let's go ahead and do that. You're going to need some of the properties that we saw in the previous video, so go back, take a look at them, make sure you have those trig properties memorized. So in this case here, the strategy, if the integral is of the form tan to the exponent m of x times secant to the exponent n of x dx, we use the following u substitution. So if the n is even, so if the exponent of the secant is even, we save a secant squared and we let u equal tan of x. Okay, so we're using the u substitution, u equals tan. And the other case is if m is odd, save a secant times tan. So the exponent of the tan is odd, save a secant times tan, and let u equal secant of x. Okay, notice this doesn't cover all our cases. So if these two conditions are not satisfied and our strategy does not apply, we're going to even look at examples where this doesn't work. Okay, so just to cover all our bases. So let's go ahead and take a look at a couple of examples. So in our first example over here, we have to evaluate the integral of tan to the 4x times secant to the 4x dx. So let's go ahead and apply our strategy. Notice the exponent of tan is even, which is not a good thing. We have a rule for when tan is odd, but we do have a rule for when secant is even. The exponent of secant is 4, it's even, so we know we have to save a secant squared, and we have to let u, apply the u substitution, u equals tan of x. So let's go ahead and do that. So this is equal to the integral of tan to the 4x times secant squared of x times secant squared of x. So I'm splitting the 4 into secant squared times secant squared. So we're saving a secant squared, that's what it tells us to do. And we're going to let u equal tan of x. Okay, if we apply the u substitution, u equals tan of x, what's the derivative? Well, the derivative of tan is secant squared, the term that we're saving. And solving for dx, we divide both sides by secant squared, gives us du over secant squared x. Okay, so this is side work. So this gives us the integral. I'm going to substitute in terms of u. Tan to the 4x, tan is going to be expressed as u, giving us u to the 4, times secant squared. There's nothing we could do about this guy. We have to leave it. This secant squared as well, we have to leave it. And dx, we could express it as du over secant squared, which cancels with this one here. Great. But the issue is that we're not expressed solely in terms of u. Notice that we have an x in here. How do we get rid of it? Well, this is one of the properties that I provided in the first video, where we have to remember, so we know that sine squared plus cos squared equals 1. For secant and tan, we know that secant squared is equal to 1 plus tan squared. And this is the property that we have to use, because we want to rewrite this in terms of u, so we want to use only tans, because we have a relationship between tan and u. So rewriting secant squared as 1 plus tan squared opens the door for the u substitution, because we could substitute the tan with u. So let's go ahead and do that, giving us u to the 4. Secant squared, I'm writing it as 1 plus tan squared du. Let me erase the property, so keep this property in mind. This is the one you're going to be using for these types of problems. Rewriting tan as u, we have the integral of u to the 4, 1 plus u squared du. And now this is easy to solve. So we're going to distribute the u to the 4, giving us u to the 4 plus u to the 6. And now we integrate each term individually, giving us u to the 5 over 5 plus u to the 7 over 7. It's indefinite, so we have our plus c. And again, we go back in terms of x. So u is equal to tan x. Let's bring the tan back. So this is tan 5x over 5. So we're replacing the u's with tans, plus tan. If you write it as tan x to the 7, something like this, that's fine. Both notations are okay. Typically, we write it in this form. And plus c. This is the final answer. So let's go ahead and keep practicing. Let's look at the next example. So in our second example over here, it says to evaluate the integral of secant cubed x times tan of 5x dx. So pause the video, give this a shot, see if you're able to solve it. So now we're using property, our second condition, the fact that the exponent of the secant is odd. So if the exponent of the secant is odd, it's telling us to save a secant tan and to use the u substitution u equals secant. So let's go ahead and do that. So I'm going to write the integral as secant squared x times tan 4x, and I'm saving a secant times tan. So I removed one of the secants and I removed one of the tans, and this is what I'm saving. Okay, now I'm going to apply the u substitution, u equals secant. U equals secant x, and now we take the derivative to get du. So du equals, the derivative of secant is secant tan dx, and solving for dx we get du over secant tan. Okay, so again, this is side work. This integral is equal to secant squared tan to the 4. Well, the secant we could rewrite in terms of u. Let's do that right away. So secant is u, so this is u squared. Tan, there's nothing we could do about it, we have to leave it. And the secant tan we have to leave as well. Secant tan. And the dx we're going to rewrite it as du over secant tan. I don't have room, I'm just going to write it here. Secant tan. And notice that the secant tan cancel. What we saved canceled out, leaving us with just the integral of u squared times tan to the 4x du. And at this stage here, you should see what happens with the tan. It's not expressed in terms of u. We want to express it in terms of secant. What do we use? We go back to our property. So we know that secant squared is equal to 1 plus tan squared. Okay, but we want tan to the 4. How do we do this? Move the 1 over. So we get secant squared minus 1 equals tan squared. And we saw this in the earlier video. From tan squared, we want tan to the 4. We square both sides. So squaring this and squaring this. Tan squared is tan to the 4, and that's equal to secant squared minus 1, all that squared. So we could express this as the integral of u squared. Tan to the 4 is going to be expressed as secant squared minus 1, all that squared. The secant, we're going to express it in terms of u. Secant's equal to u, so I'm just going to replace my secant right away with u. So it's secant squared or u squared minus 1, all that squared. Okay, so I just transformed this right away, du. Now it's expressed solely in terms of u. And we could go ahead and solve this. So just a bit of computation, we open up the bracket. We have our u squared. This is a binomial squared, so we expanded u squared minus 1 times u squared minus 1, giving us u to the 4 minus 2u squared plus 1. And now we distribute the u squared in, giving us integral of u6 minus 2u4 plus u squared. And now we integrate each term individually, giving us u to the 7 over 7 minus 2u5 over 5 plus u3 over 3 plus c. And lastly, as always, we come back in terms of the variable that we started with, so we come back in terms of x. So this is just secant. I don't have much room, so I'm just going to slip it in here in the box. We have secant 7x over 7. This is supposed to be written on one line. I'm just going to write it this way, minus 2 secant to the 5x over 5 plus secant cubed x over 3, and all this plus your constant c. Okay, so I apologize for the notation, but this is the final answer. Okay, let's take a look at the next example. So in the next example over here, we have to evaluate secant x dx. How do we do this? Well, again, we could think of it as secant x times tan to the 0x dx. Let me do it on black. Okay. So the exponent of the secant is a 1, which is odd, and the exponent of the tan is a 0, which we can think of as even. We can't use our property here. right? Because our property says we could pull out a secant squared if our secant is even, or we could pull out a secant tan if the exponent of the tan is odd. This doesn't satisfy any of our criteria. How do we solve this? So we have to get a bit clever. So in order to solve this problem, the trick here, which ends up working, is to remove the tan 0 of x. But for just the secant, you're going to multiply the top and the bottom by secant plus tan. And this ends up working. Let's see why. So we have secant x, and we're going to multiply it by secant x plus tan x on the top and bottom. Why am I allowed to do this? Well, it's just a fancy way of multiplying by 1. So we're just adding this term here, but this is the same thing as this. Anything divided by itself is 1, so we're just multiplying by 1. We're not really changing the integral. We're just changing the way it looks. And on the top, we could distribute the secant, giving us the integral of secant squared plus secant tan. All this over secant plus tan. Why is dx? Why is this a good thing? Why does this open the door? So the observation that you have to make, if you want, you can pause the video, give this a shot, think about it a bit. But this is a good thing because we could solve this with a u substitution. Try to think about what you would let your u be in this case to solve this integral. So the answer to that, you're going to let u equal the entire denominator. Secant plus tan. Why? Why are we letting it equal secant plus tan? We'll take its derivative. What's the derivative of secant and tan? Well, the derivative of tan is secant squared, which happens to be sitting on top, and the derivative of secant is secant tan, which also happens to be sitting on top. So this ends up working. This allows us to solve this type of problem. So the derivative of secant is secant tan, and the derivative of tan is secant squared dx. I'm not going to write it, but we could divide by this whole thing to isolate for our dx. Divide by all this. So we could rewrite this as the integral secant squared, whatever's on top stays, secant squared plus secant tan divided by secant plus tan on the bottom, we're replacing it with u, so it's divided by u. And on top we have dx, which is equal to du divided by this whole thing. So I'm going to write du divided by secant squared plus secant tan. Running out of room, but notice that the secant squared plus the secant tan, as I mentioned, just end up canceling each other. It works out nicely, and we're just left with the integral of 1 over u du. That's all we're left with, and this we know the integral of 1 over u. If you're thinking of using power rule, that's wrong. We can now use power rule. You're going to get a division by 0. This is ln. This is equal to ln of u. It's indefinite, so plus c. And what's our u equal to? Secant plus tan. So the integral of secant, you just have this memorized, or if not, you have to repeat this process, which is hard to start off with. But once you know this trick, the secant plus tan, you multiply by secant plus tan on top and bottom. It's not too bad. But I think I would just have this memorized and let u equal the secant plus tan. So the answer is ln of secant plus tan. Okay, and it's indefinite, so we have our plus c. So the integral of secant is ln of secant plus tan plus c. Let's go ahead and take a look at another example. So in the following example, I'm going to show you how to integrate secant cubed of x dx. Do not pause the video. This one I will not ask you to try this on your own. This is a very difficult problem. So let me show you how to go about it. Because again, secant cubed x times tan of 0x, it doesn't follow our strategy that we spoke about in the beginning. So we want the exponent of secant to be even, or we want the exponent of tan to be odd. If we don't have that, we have to get clever. How do we solve integral of secant cubed? So the trick is we have to apply an integration by parts. Okay, so that's how we will begin this. So let u equals secant, and let dv equals secant squared dx. Okay. So remember, for integration by parts, we take the derivative. So the derivative of secant is secant tan. And what's the integral of secant squared? Well, it's just tan. So integration by parts, remember, it's the integral of u dv is equal to minus the integral of v du. Okay. So we're going to follow this pattern. So this, what we have in blue, the integral of secant cubed is equal to u times v. So we follow this pattern. We go top left to bottom right, and then bottom right to bottom left. So u times v, in this case, secant times tan. Oh, sorry, there's no dx here. There's a dx here. That's poor notation, I apologize for that. So whenever you have a du, you have your dx. Whenever you have your dv, you have a dx. Here it's v, so there's no dx. So secant times tan minus the integral of v du. So the integral of v tan x times secant tan. So since there's another tan, I'm just going to write tan squared times secant, and we have our dx. Yeah, so here we have the integral of tan squared secant x. So what we could do is apply the fact that secant squared is equal to 1 plus tan squared. So we know that tan squared, if we subtract over to 1, tan squared is equal to secant squared minus 1, giving us secant tan. That's outside the integral sign, so that's fine, minus the integral tan squared, we're going to write it as secant squared minus 1. And it's that times secant x dx. Okay. So using our property, we switched it into this form. And now what I'm going to do is distribute the secant. So we get secant x tan x minus the integral. We have secant times secant squared, which is secant cubed, minus secant x dx. Okay. Why is this a good thing? Well, first of all, I could deal with each term individually. So since we have a minus in the front, I'm going to distribute it to both of them. So this term here is going to be minus, this term is going to turn into a plus. And I'm going to just take the integral of each term. So I distributed the negative, and at the same time, I'm dealing with the integral of each term individually. Integral of secant x, we know the answer to this. We saw that the integral of secant x was the ln of secant plus tan. So this part's okay. But what's this? How do we get the integral of secant cubed? Well, notice that's right back where we started. So did we fall into a loop? No, this isn't a bad thing. What we could do here is notice that the integral of secant cubed is equal to this whole thing, right? Each step that we went through, we eventually got to this part. So what we could do is take this piece of the integral, the negative integral of secant cubed dx, and bring it on the other side, back to where we started. So since it's minus on this side, I'm going to add it over on the other side. It's going to give me 2 integrals of secant cubed dx on the left hand side. So I brought this one over back to where we started, and what we're left with is secant x tan x, and this piece here, the integral of secant, we saw was just ln of secant x plus tan x plus our c, and the last step would just be to divide it by 2. Okay, so this was an integration by parts. We saw this with e to the x times sine, or e to the x times cos, where it's recursive. It comes back to where we started. We have to do this loop, and since we had the times 2 here, we're just going to divide everything by 2. Okay, so the integral of secant cubed x dx is equal to secant x tan x plus ln of secant x plus tan x, all that divided by 2, plus our constant. Okay, so we're combining trig integrals here with integration by parts, and this is the answer. So let's go ahead and look at the next strategy. So here we're looking at the strategy if the integrals of the form, the integral of cotangent to the exponent m times cosecant to the exponent n of x dx, we apply the following u substitution. If n is even, if the exponent of the cosecant is even, you save a cosecant squared and let u equal cotangent. If m is odd, the exponent of the cotangent is odd, you save a cosecant times cotangent and you do the u substitution, u equals cosecant. Okay. If this looks familiar, well, it is. This is the exact same strategy that we saw earlier in the video. We're just switching tangent, switch the word tangent with cotangent, and switch the word cosecant for secant. And it's identical. It's the exact same strategy. Notice that when we had secant, if the exponent of the secant was even, we took out a secant squared. Here we're just switching it to cosecant squared, and we let u equal tan. And in this case, we're letting u equal not tan, but cotan. So just add a co in front of the properties that we saw in our first strategy, and we have this one over here. So it's essentially the same strategy again. Just now, instead of tangent, it's cotangent. Instead of secant, it's cosecant. Okay, so let's take a look at a quick example. So in our final example over here, it says to evaluate the integral from cotangent cubed 2x times cosecant cubed of 2x. So the first thing to notice is that the angles are different here. Instead of x, we have 2x. So the first thing I do right away, I get rid of it. I use a u substitution. So let u equal 2x. We take our derivative du equals 2 dx. Solving for dx, we divide by 2 on both sides. And that's the first thing I'm going to do. So now we're left with cotangent cubed of u times cosecant cubed of, again, u. And dx is being replaced with du over 2. The division by 2, I'm just going to sit in the front. Just not to work with the constant. Okay. The coefficient, 1/2. So now we reduced it to a cotangent cubed u and a cosecant cosecant u cubed. Since they're both cubed, we apply our strategy. Since the exponent of tan is odd, or cotan is odd, we save a cotangent times a cosecant, and we let u equal cosecant. So let's go ahead and do that. Let's write it down here. So we have cotangent squared of u, cosecant squared of u, times cotangent u, cosecant u. Again, you don't have to do this, but this is just to emphasize on the fact that this is going to cancel du. And this is the same as this, right? The cubes just, if you multiply these two, you add the exponents, you get back what you started. Okay. And now we apply the u substitution. But since we use the letter u again, let's call it something else. Let's call it a z substitution. So let z equal, we said to cancel this is cosecant u du. Sorry. Let z equal cosecant u. And the derivative of z is equal to the derivative of cosecant, which is negative cosecant cotangent. So essentially what changes when you take the derivative of cosecant, because it starts with a c, this is something we saw in an earlier video, a negative comes out. Okay. So this is our z substitution. Applying it, we get 1/2 cot squared u, cosecant squared u. This piece stays. But I'm just going to cancel it right away because we know du is going to be equal to dz divided by this whole term. And this whole piece here is going to cancel with this. So just to save space, I'm going to write it as negative, put the negative from here in the front, and I'm just going to write dz here because I know it's going to cancel with this piece that I saved. And the other thing is cosecant u, we could rewrite it as z squared. So we're almost entirely in terms of z. We just have to get rid of this cotangent u. How do we do that? Well, again, we go back to the property. We know that secant squared x equals 1 plus tan squared. Well, again, switch secant to cosecant, and we have the same property. Cosecant squared equals 1 plus cotangent squared x. Okay, so this is the exact same property, and we solve for cotangent squared. So we bring over the 1, and we get cotangent squared is equal to cosecant squared x minus 1. So let's go ahead and substitute that into here. Just gonna erase this to give myself room. This is equal to negative 1/2 integral cotangent, we said, is cosecant squared minus 1, but cosecant is just z. So I'm going to rewrite this as z squared minus 1 times z squared dz. Distributing the z squared, we get negative 1/2 integral z to the 4 minus z squared, and that's negative 1/2 z to the 5 over 5 minus z3 over 3 plus c, and the last step, we substitute our z back in terms of x. Okay, so let me just erase this to give myself some room and do it up here. Apologies. I'm just going to continue up here. This is equal to negative z is going to be replaced with cosecant u to the 5 over 10. I'm distributing the negative 1/2 plus 2 negatives make a positive. 1/2 times a third is over 6, and z is being replaced with cosecant u to the 3 u plus c. Okay. If you leave your answer like this, again, it's wrong because we didn't start in terms of u. We started in terms of x. So we have 2 substitutions to go back into. So you have to bring back the 2x as well. So this is negative cosecant to the 5 of not u, but u is equal to 2x. We start in terms of x, we finish in terms of x. Over 10 plus cosecant cubed of 2x over 6 plus c, and this is the final answer. Okay, so I hope this video helped. I hope you have a better understanding of trigonometric integration. We're going to need this when we start trigonometric substitution, which we'll see in the next video. So keep practicing. I wish you the best, and I'll see you in the next one.